This is an additional lecture that I have added to the course after I received some feedback from students because some formulas were not completely clear. And let me tell you that these students were quite right in the sense that sometimes I tend to motivate things intuitively, but probably not sufficiently enough without being too rigorous. So when you lack some rigor, it is definitely something that can happen. So when you lack some rigor, you're going to lose some mathematical insights that allow you to understand the subject and in general the topics. Anyway, let me tell you that first we are going to consider the following function, the sine of omega t. In particular, I want to show you some formulas and in particular how to interpret some formulas that you will see in the following lecture. So we will be interested in integrals of the following form. Integral of the sine, d omega, so in this case we are integrating over omega, but it's not really important. You can also integrate over t and treat this other variable as we treat t in this video. So in this video, I'm integrating over the omega, which we think of as the frequency, and t is the variable of time. And we're going to integrate from minus infinity to plus infinity. Now, when you have such integrals, you have to be very careful because when you integrate such oscillatory functions, and for example, if you put them on a calculator like Wolfram or other websites, they will tell you that if you want to calculate this integral here has no result. No result. And similarly, if you had the cosine instead of the sine, so integration from minus infinity to plus infinity of the cosine of omega t d omega. So this also has no result. In particular, by no result, I mean that they do not converge. Anyway, with the right interpretation, thanks to the Fourier approach, we will see that we can attribute a value to such integrals. This is what I want to show you. This is what I want to show you in this video, and you will also see some other results in the following video and also in the subsequent ones. So you will see something more and probably even more precise than here, that we are going to use some intuition. But I want to motivate some results that you will see in the following videos so that those results will not be confusing to you. Because if you think about it, well, it makes sense that such integrals do not converge, right? Anyway, let's start from the sine of omega t. And in our case, we think of omega t, so the sine of omega t, as a periodic function where omega belongs to the interval minus L over 2, L over 2. So if you want, you can call this L whatever way you want. You can call it capital T or whatever way you want. So you can choose a label. For this, we will call it L. L over 2 minus L over 2. And we think that this function here is periodic inside this interval. So it's as if we are expanding in a Fourier series such a function. So in our case, omega is a continuous variable, and we think of the variable t as a discrete variable. So t will be t sub n. T sub n will be discrete, and it will be equal to 2 pi n divided by L. So if you think about it, when you consider a function which is periodic in such an interval, and our continuous variable in this case is omega, in this case, the conjugate variable to omega is t. So for t here, we will have a discrete quantity. So I could have done the opposite. So you could have considered t as the continuous variable, and of course, then you would have gotten that omega would have been the discrete variable. But this is something that's not really important at this point. So we consider omega to be the continuous variable and t to be the discrete variable. You know that as L goes to infinity, the discrete variable Tn will approach the continuous variable t, so it will become closer and closer to a continuous variable. So this is what we will think in this lecture. We will think that L is very large in such a way that we can consider actually this Tn to be a continuous variable. And we are interested in calculating the following integral. So we integrate from minus L over 2 to L over 2 the sine of omega t. We know that t is equal to Tn. We integrate it over omega. Well, if Tn is non-zero, we can calculate this integral, because if Tn was equal to 0, then of course this sign would be 0, and therefore the result of the integral would be 0. But if Tn is not equal to 0, we can easily calculate the integral to be minus the cosine of omega Tn divided by Tn from minus L over 2 to L over 2. Now this is equal to minus 1 over Tn, and then you have the cosine of L over 2 Tn minus the cosine of minus L over 2 Tn. But now, since the cosine is an even function, the cosine of minus something is equal to the cosine of plus something. So here we can also put a plus, because the cosine is an even function. Therefore, you can see that these two here will give you 0. So you will have 0, assuming that indeed Tn is not equal to 0. So the result of the integral is 0, but it would be 0 also if Tn were 0, because you can see that if Tn is equal to 0, the sign of this would be 0. So when you integrate a function which is 0, you get 0, right? So the result of this integral is equal to 0, even if you think that L is very large. So in this sense, we can say that the integral from minus infinity to plus infinity of the sine of omega t, as we let L go to infinity, this Tn will approach a continuous variable. Therefore, here we can set this integral to 0. But you have to be careful and interpret this result in such a way that, for example, here you have minus a certain interval, and here you have plus that interval. So you have some kind of symmetry, which allows you to say that the integral of the sine over a symmetric interval will give you 0, even if the width of this interval goes to infinity. So even if you integrate from minus infinity to plus infinity. This is the first result that I wanted to show you. Then there is also another result that I want to show you, and it is a very similar one, because now we are going to integrate from minus L over 2 to L over 2. Instead of the sine, well, you can guess it, it's the cosine of omega Tn d omega. Now, here we can assume that Tn is non-zero, because otherwise the cosine would be equal to 1, and therefore, as a result, you would get L, right? When you integrate 1 from minus L over 2 to L over 2, you get L over 2 minus L over 2, so you get L. And as L goes to infinity, of course, the integral would diverge, therefore Tn would, the cosine of 0 would be 1, and you would have a divergent integral. So now we are assuming that Tn is non-zero. So we can say the result is L if Tn is equal to 0, which means that since we think that L goes to infinity, we will get infinity as t is equal to 0. Because when L goes to infinity, this Tn will become a continuous variable, so this would be 0. But if Tn is not equal to 0, we can calculate the integral in the following way. So we get the sine of omega Tn divided by Tn. We evaluate it from omega equal to minus L over 2 to L over 2. And this is equal to, you get, well, in this case, the sine is an odd function. Therefore, here you simply get twice the sine of L over 2 Tn divided by Tn. So here you can see also from this calculation that as Tn goes to 0, the limit of this as Tn goes to 0 is simply 2 times L over 2 Tn divided by Tn, which is equal to L. So you still get the result above. So basically you can say that the result of the integral is this, even if Tn was equal to 0, because in that case you can take the limit. But anyway, we know that as t is equal to 0, you get this result, whereas when Tn in general is not equal to 0, you get this. Now, at this point, we know that Tn has the following expression. So Tn is equal to 2 pi n divided by L. And we can substitute it there. So we get 2, the sine of L over 2 times 2 pi n over L. And then, of course, we divide by 2 pi n, and we can multiply this by L. Since if we divide this by L, of course, it's as if we multiply this by L. Now we can simplify this 2 with this 2 and this L with this L. So we get, and we can also simplify this 2 with this 2. So we get sine of pi n times L divided by pi n, like this, right? But now, at this point, if n is not equal to 0, because if n is equal to 0, we know that Tn is equal to 0 in that case. So n here cannot be equal to 0, so it can start at n equal to 1, then we can go to 2, 3, and so on. You can see that in that case, the sine of pi n, well, is equal to 0, right? So here we would get 0 divided by something is still equal to 0 multiplied by L. We are thinking that L is very large, so we take the limit, but that's a limit. It means that L is something that does not diverge in principle, right? So we multiply a very large number by 0. So this is exactly 0. So when we multiply even a large number by 0, we still get 0. So it means that the result of this integral here is equal to 0 everywhere except when Tn is exactly 0. So we can say, okay, now we take the limit as L goes to infinity, so we can write integral from minus infinity to plus infinity of the cosine of omega. Now, instead of Tn, I will write T, because now this will become a continuous variable as L goes to infinity, d omega here. We know that basically the result of this integral is infinity if t is equal to 0, and it is equal to 0 if t is not equal to 0. So in particular, in the next video, I will say more about this, and I will tell you that this is related to the Dirac delta. And you will also see another video, another subsequent video that will show you a different derivation, because this is more intuitive and little less rigorous. But anyway, I wanted to show you this lecture here. I wanted to show you these concepts in this lecture because they are important for you to understand a little bit more the intuition behind what I'm going to say also in the following video. Let me tell you that if you start, for example, from this result and you accept it, well, you can also derive what we derived here by taking the limit as L goes to infinity, but you can do it in another way. So if you accept such a result, and please let me stress again that this result here should be interpreted appropriately, because in general, for example, if you consider the integral from some point A to another point B of the sine omega t d omega, and you let A go to minus infinity and you let B go to plus infinity. In this case, you have to be careful, because if the interval is not symmetric, you cannot really say that the result is 0. So This is also another way for you to recognize the fact that you have to pay attention to when you write such integrals and you have to interpret them in the right way, because otherwise you're just going to get confused. So this is why I want to stress these concepts in this video. Anyway, if you start from this and you interpret it in the right way, and now assume that you make the following substitution. From omega, we go to the variable omega tilde. So we define omega tilde in the following way. Omega tilde is equal to omega minus pi divided by 2t. So this is a substitution that we do. And pay attention to the fact that if we want to make such a substitution, we have to be sure that t is non-zero. Otherwise, this does not make sense. So let's make the substitution. Here we have an integral from, as omega goes to minus infinity, omega tilde still goes to minus infinity, because this is just a constant, a finite constant, because we assume that t is not equal to 0, so we start from minus infinity. And as omega goes to infinity, we still go to plus infinity. Now here we have the sign of omega. Now omega is equal to omega tilde plus pi over 2t. So here we have omega tilde t plus pi over 2, because we can simplify the t multiplied by this t. Simple as that. And then you have the differential of omega, but the differential of omega is equal to the differential of omega tilde. It's very simple, because omega tilde is equal to omega minus a constant. So their differential is still equal to I mean, it's the same, right? So d omega is equal to d omega tilde. At this point, you can easily see that the sign of omega t, omega tilde t plus pi over 2, well, that's equal to the cosine of omega tilde t. So basically here you get integral from minus infinity to plus infinity of the cosine of omega tilde t d omega tilde. You can see that you can derive the fact that this should be 0, since we started from this result here, which was equal to 0, therefore also such an integral here should be 0. Remember that we assumed that t is not equal to 0. So of course, if t were equal to 0, you cannot make this substitution, and you can't say that this integral is equal to 0. And you already know that, right? It's quite intuitive, because if t were equal to 0, you have to integrate the function which is equal to 1. So you get an infinity there. Simple as that. So in here, you can see that with the right interpretation, we can attribute a value to such integrals here. And with the sign, we were integrating, in this case, from minus L over 2 to L over 2, and then we let L go to infinity. And we derived the result by taking this limit, and probably this one here is more intuitive. Because otherwise, if I write it like this, with this infinity here and minus infinity here, and you don't have the right interpretation, well, you can get confused, and you might believe that there is a mistake, which, I mean, it's something that is understandable. So this is how you should interpret these formulas, especially when you will see them in the next video.